All right. Last time we talked about sine and cosine primarily, but I told you that we also want to know how to do trig integrals involving products of powers of secant and tangent. Okay. And again, the goal is to come up with some kind of plan of attack, just like we did in the case of sine and cosine. We had slightly different approaches depending on the so-called parity of the powers. When I say the word parity, I'm talking about oddness or evenness, yes? And depending on the parity of the powers, some nice alliteration going on there, we would do different things. If there was an odd power on sine or cosine, then we were in business and we could simply proceed via U substitution. If, on the other hand, both the powers happened to be even, then we had to resort to something that was slightly more complicated, namely utilizing the half angle identity, okay? But we could do it. Before we get going here, one reminder, namely today at midnight, or not midnight, actually 11:55, so don't try to do your homework in the last 5 minutes before the clock strikes midnight. Please do have that section 1 done. I think the next one is due, section 2 is due on like the 26th or something like that. Any questions on that before we move on? Questions? By the way, we'll have a quiz at some point next week. I haven't decided when, but it will probably be on Wednesday or Thursday or Friday. Okay? Just kind of depends on where we land. I want to get to a place where I can, just give a nice check of where you guys are in your thinking. Okay? Any questions? All right. Well, last time I drew a picture that was supposed to be a rendering of what's happening with the unit circle as it pertains to trigonometry. Showed you all the links. Basically, all of trigonometry lives in that picture, all of it. Even complicated things, like the half angle formula, for instance. May not be clear to you why the half angle formula follows from that picture, but it does. And it's sort of amazing. I would just challenge you to try to come up with some of those identities by thinking about that picture geometrically. Okay, so look, we want a plan of attack. First of all, the only identity we have to remember here is that secant squared is 1 plus tangent squared, all right? Good, right? Last time we had to remember 3 things. Now we just have to remember 1. But the plan of attack, on the other hand, is a little bit more complicated, okay? So here it is. If the power of secant is even and positive, okay? So just, wait, don't read it. Just don't read what's there. Just think about it for a minute. If the power on secant is even, then it makes sense that you would want to peel off a couple of secants. Does that make sense? A secant squared. What would be left as a power on secant, since I started with an even power and I peel off a secant squared, what would be left would still be even. And therefore, I could replace all of those secants. So if it was like secant to the 10th was left, I could write that as secant squared to the 5th, yes? And then I could simply replace secant squared with 1 plus tangent squared, yeah? And then all that would be left would be tangents with this lone secant squared factor dangling off the end. And therefore, I could do a U substitution. You see it? Okay? So that's kind of like the easiest case. If the power of secant is even and positive, save a single secant squared factor, convert the rest of the secants to tangents, expand, and integrate. Basically, what I didn't write there was, do a U substitution. Okay? Second, if the power of tangent is odd and positive, oh, okay, all right. If the power on tangent is odd and positive, so this is like a second priority. Look, I mean, if the power on secant is even, just do number 1, okay? Okay, is a second, if it's not, then you kind of hope that the power on tangent is odd. Because if that happens, and you have an extra factor of secant sitting there, then you can take a secant and a tangent and put it on the end. And since the power on tangent was odd to begin with, and I just made a secant tangent and put that on the end, what is now the power on secant, odd or even? It's even. And therefore I can convert all those things to secants. And what could I do at that point? U substitution. I could put U equal to secant. And what's the derivative of secant? Secant tangent. Okay? Okay? Third, if there are no secant factors and tangent is even and positive, convert a secant squared factor to a secant, or a tangent squared factor to a secant squared factor, and then kind of deal with that. Like you want there to be both secants and tangents there. Does that make sense? Like you basically take a tangent squared factor and convert it to a secant squared factor, and then you sort of proceed from there. You may have to repeat that because tangent squared plus 1 is equal to secant squared, which means tangent squared equals secant squared minus 1. So you're going to keep getting like powers of tangent, but you can kind of reduce those down. You'll see what I mean here pretty soon. If there is only an odd power of secant, you have to use integration by parts. You guys, we already did that, right? Remember, what did that was the gnarly thing we did at the end of section 2, wasn't it? Like secant cubed. Remember we did that? We did secant. We had secant to the 5th. We would have to do some pretty awesome integration by parts, okay? But we could actually pull it off. Otherwise, if none of these situations apply, you just out of sheer desperation convert to sines and cosines and hope for the best. Okay? But this is at least a plan of attack. Okay? All right. So let's do some examples, shall we? Let's see here. Yes, sir.
Has there ever been a time that you've actually gone completely to step 5 and not been able to figure it out?
I probably. I don't recall off the top of my head, but generally speaking, there's usually something that you can do. But I feel like even in the last case, permanent sines and cosines, there's so much you can do with trig functions that you can almost always get it to work somehow. But yeah, let's look at some examples here. Okay. Here, I'm gonna have to the world. So there we go. Over to that. Hey, are you seeing the whiteboard right now, Trent?
Yeah, it's just blinked right now, but yeah.
Okay, good. Exactly what I wanted. Okay, so here's an example. Okay, and I'm going to let you kind of work on this on your own at first, but in the integral of tangent to the 5th of x, secant to the 4th of x dx. Okay, now, I gave you your whiteboards. Think about that for a minute, okay? And maybe talk to your neighbor for a minute. Try to work on that. Think about what we just said on the previous screen as guidelines. Think about what you might do. Now remember, tangent squared plus 1, tangent squared of x plus 1 is equal to secant squared of x. That's sort of the key identity that we're going to be using, the Pythagorean identity involving secants and tangents. Okay. Well, any ideas? All right, let's hear it.
Okay, so I mean, you start with tangent to the fifth, secant to the fourth, so you change secant to the fourth to 1 plus tangent squared times secant squared, and then you can just use u equals tangent and solve from there.
Okay, so really what you did is you broke up this as secant squared of x times secant squared of x dx, right? And then you basically did this. You took this guy and put it right there, yeah? Or actually, oops. Oh man, that thing really just obliterated the whole thing, okay? You put it basically there, and you save the secant squared as kind of a u sub factor. So what you're saying is you went, okay, this is the integral of tangent to the fifth. I'm writing in red right now, I realize, but that's all right. And then you multiply this by tangent squared plus 1. Okay? And then it's secant squared of x dx. Okay? And what are you putting u equal to? Yeah, if you put u equal to tangent of x, you know that du is going to be secant squared of x dx. Exactly. Okay? So this thing becomes the integral of, look at that, that's perfect, right? The integral of u to the fifth times u squared plus 1 du. And what do you do? I mean, look, I'm not trying to insult your intelligence or anything, but what would you do to finish the job here? Right, so you distribute that thing through, you end up with u to the 7 plus u to the fifth du equals, look, and now I really don't want to insult your intelligence by finishing that, yeah? Well, it would be 1/8 u to the 8th plus 1/6 u to the 6th. You would plug u back in, yeah? Plus a constant, okay? Okay? Is that the only way one could have proceeded? Or is there another way you could have proceeded?
Probably without the easiest.
Did anybody else try something else? Did anybody else try? Yeah. Yeah, because the power on tangent, remember this actually falls into the first two of the guidelines we had, right? We also could have said, hey, the power on tangent is odd. And let me just kind of go over to the next one here. The power on tangent is odd. Okay, so this was tangent to the fifth of x, secant to the fourth of x. The power on tangent is odd, therefore, I could have said this is like tangent to the fourth of x. I also have to peel off a factor of secant, you understand? So I would write secant to the third of x, and then off the end, it would be secant x tangent x dx. Yeah? Okay. And now what? Now what are we thinking? What are we going to do? Yeah, convert the tangents to secants, right? So like tangent squared of x plus 1 is equal to secant squared of x, right? So that means that tangent squared is equal to secant squared minus 1. So I'd kind of rewrite this as tan squared of x squared, secant cubed of x, secant x tan x dx, right? So this would be the integral of what? What would I put in here? Secant squared of x minus 1 squared, secant cubed of x, secant x tan x dx. And now we put u equal to secant of x. Exactly. And du is secant tangent. Secant x tangent of x. Dx. Okay, so this thing would become the integral of u squared minus 1 squared, u cubed, du. And you would have to expand this guy right here, right? So you would expand this to kind of finish the job, right? So let me just say, etc. Expand that, multiply through the u cubed, do the antiderivative, plug u back in, put a little plus c in there, done. Now, the antiderivative is going to look different in this case because it's going to be a combination of powers of secant is the answer, whereas in the last problem, it was a combination of powers of what? Tangent. Yeah, that's right. So the answer is just going to look different, but they are trigonometrically equivalent to one another. Okay? All right. Any questions on that? Well, okay, let me see. Yeah, there we go. Okay, let's do another one. And this time, let's just look at a singular power or just a power of the tangent function. So what would you do if it was like tangent to the 5th of x dx? Do you remember what the guiding principle was in that case? What was the guiding principle there? Convert the tan squared to some kind of secant squared situation, right? So you go the integral of tangent cubed of x times tan squared of x dx. And then what you do is you say, okay, well, this is the integral of tangent cubed of x. What's tan squared? Yeah, so this is secant squared of x minus 1. And I think on that guiding principle, I said you may need to repeat stuff. You need to kind of expand this and then repeat. So we expand this thing out. Okay, so and look, when we do that, we're going to get the integral of tangent cubed of x, secant squared of x, and I'm going to split this up, dx, minus the integral of tangent cubed of x dx. Do you know how to handle the first integral? You guys understand what I did? I just distributed through the tangent cubed and broke it up, yeah? Do you understand how to do the first of these two? Yeah, you would just simply put u equal to tangent. The derivative of tangent is secant squared. Okay, so look, I'm just going to write that under here. So under this one right here, you put u equal to tangent of x. Du is going to be secant squared of x dx. And so this integral is going to turn into, when we do that, this will be the integral of u cubed du. Good grief, right? Challenge us, will you, right? That one's easy to do. But the problem is, what about this tan cubed of x? This is what I meant when I said you will have to kind of repeat the process at times and systematically decrease the power on tangent. So what am I going to do? Do it again. Why not? Okay, so we're going to write this as tangent of x times tangent squared of x, which let me just write in what tangent squared is. Isn't that just secant squared minus 1? Yeah? Tangent squared, right? So it could, because that, my friends, that is tangent squared right there. That's tangent squared of x, yeah? Okay, and this is dx, okay, which equals, oh man, I'm gonna have to go to the next slide here. Okay, so this thing equals the integral of u cubed du minus the integral of, oh man, I'm gonna have to go back and I already forgot what I wrote. Right, it was tan x times secant squared minus 1, right? Okay, So tan x times secant squared minus 1, right? Yeah, equals the integral of u cubed du minus the integral of tan x secant squared of x dx. And what is it? It would be, is it a minus negative? Is that what that one was on the previous slide? It was minus negative, so it's like a plus the integral of tan x dx. Does that comport with what I had on the last slide? Yeah. Okay, so how would I deal with this? I already used u, okay. Just to be precise, I'll use a different letter here. What am I, okay, I'll say v. What am I gonna put v equal to? Tan x dv is secant squared of x dx, okay? And by the way, this guy right here, you should, okay, let me just say. So this is going to be the integral of u cubed du minus what? Integral of v dv plus, now here's the thing. You should know what the antiderivative of tangent of x is. We did that, remember? You remember? So this one right here is 1/4 u to the 4th. This guy is minus 1/2 v squared. And then it's plus, or hang on a second, actually. What is this? You guys tell me. Not quite. It was minus the natural log of cosine. Actually, that's right. Natural log of c is the same thing as natural log of secant. You understand? Minus natural log of cosine. If you put the -1 up there, 1 over the cosine is secant. That's cool. We'll write it that way. Why not? Natural log absolute value of secant of x. Yes, that actually works. Okay. Plus a constant. Now, u and v are equal to something, right? So I'll just say etc. just so we can move on. But there it is. Okay. So natural log of secant minus natural log of cosine, those are the same thing. You understand? We had those formulas back there. I actually like, hey, I like natural log of secant. Why does the book have minus natural log of cosine? Just have natural log of secant, then it kind of reminds you of the antiderivative of secant. Remember what the antiderivative of secant was? Natural log of not just secant, was the secant plus tangent. Yeah? So that's interesting. Oh, awesome. Yeah, that's right. Yeah. Natural log of secant actually does work. Okay. Okay. Moving on. Moving on. Okay. Let's look at another example here. What about a power of secant? Oh boy. Okay. What about the antiderivative of secant? We already did secant cubed. You understand what I'm saying here? Remember that? Yeah, that was fun, wasn't it? What if we do secant to the 5th? So think about it. We already know, let me just say, we already know what? The antiderivative of secant of x dx. We know the antiderivative of secant squared of x. That was trivial, right? Of course, I can write that down right now. That's tan x, right? What was the antiderivative of secant of x? Yeah, I'm running out of space here. Okay. Okay. And secant cubed, that was fairly intense. Remember?
No.
It was secant x tangent x plus natural log of secant x plus tangent x absolute value all over 2 plus c.
Whoa, nice. Okay, so it's 1/2. So it was 1/2, and then it was secant x tan x, right? That's what you're saying? Plus natural log absolute value of? Yeah, that rings familiar to me. Turns out that actually comes up a fair amount, but we at least have these guys. You know what I'm saying? Yeah? So, what do you think we could do in this particular case? We have secant to the power 5. What do you think we can do?
I want to make it tangent, but I don't think that works.
Okay, let's do that. Okay, so if we go, this is equal to the antiderivative of secant cubed of x times secant squared of x dx. All right, now what? Integration by parts, because didn't we have to resort to integration by parts in the case of secant cubed anyways, right? Yeah. I don't think it's going to be helpful, because think about it. If I were to right now replace secant squared with 1 plus tangent squared, what am I going to end up with? Think about it. I'll have an odd power of secant and an even power of tangent, which doesn't fall into either of those guiding principles above that were in the first part. Does that make sense? So you're like, well, that's the opposite of either of those, so that's not good. So it seems like integration by parts is something we ought to try. Now, we actually do know antiderivatives for both secant cubed and secant squared. You know what I'm saying? We actually know both of those, but one of them is clearly easier. You know what I mean? Which one is clearly the easier one to deal with in terms of finding an antiderivative? Yeah, secant squared. So let's let u equal secant cubed of x. And let's let dv equal secant squared of x dx. Then du, what's du going to be?
Secant squared x tangent.
3 secant squared of x, that's the outside, right? Use a chain rule. Derivative of the outside, 3 that squared times the derivative of secant, you better not forget that, is secant tangent. Secant x tan x.
Can you combine that and make it 3 secant?
Yes, you could actually write that as just 3 what?
Secant cubed x tangent x.
Yeah, secant cubed of x tan x dx. And what's v? Tangent of x. How easy is that? The hard part was the taking of the derivative, okay? Okay, so remember, integration by parts says that this is going to be equal to, right? You go u times v, right? You go u times v, yeah? Okay. So u times v is secant cubed tangent of x minus the integral of v du. Minus the integral of v du, right? So now we look at these two guys right here, right? So minus the integral of v du. Hey, so there's a 3 here. Okay, integral of, oh man, it's going to be secant cubed what? Right, you kind of multiply those two things together, you get secant cubed tangent squared.
Wait, doesn't this become circular?
Does it become circular?
Because if you make tangent squared x 1 minus secant squared x, then you'd have a new point, but then you'd also go back to the secant 5x, I think. Might be wrong.
So what you're saying, okay, so what you're saying is if you replace, so what are you thinking about replacing now?
So if we took tangent squared x and made that equal to 1 minus secant squared x, then when we
Not 1 minus secant squared minus 1.
or, sorry,
Yeah,
secant squared x minus 1, when we multiply that out, the first term would become secant 5 of x, which would keep going back to what we originally started with.
yes.
So,
Well, how is that circular though?
well, because then we can make the I equal.
Well, okay, but it's not, right, it gets back to the original, but that's a good thing in this case. Do you know what I'm saying? It's actually a good thing. So yes, that's what I was hoping you were saying. Okay, thank you. So the suggestion is the following. You go to tangent squared and you replace it by what?
Secant squared x minus 1.
Right, secant squared of x minus 1. Okay, so this secant cubed would go through this. You might say to yourself, you idiot, why would you do that? You're going to end up with secant to the 5th, which is the very thing that you started with. But it's also going to have a minus 3 attached to it, whereas the thing on the other side has a positive 1 attached to it. Do you know what I'm saying here? Okay. So yes, that is good. Okay, so what I'm going to do is, please, help me out here. If you have this written down, you can help me remember what to write on the next screen. You know what I mean? In fact, I'm just going to write it right here. You know what I mean? Okay, so this is going to be secant cubed x tan x minus 3 integrals of what? Secant to the 5th of x dx. Minus negative is what? Plus 3 integral secant cubed of x. Oh man. Yes. Okay. So how is that helpful? Well, let me just kind of write it on the next slide just to help us out. So please, keep track of that for a minute, just for a minute. Yeah. I'm going to rewrite it over here. So what we have here is the integral of secant to the 5th of x dx is equal to, what was it again? Secant cubed x tan x minus 3 of these integral secant to the 5th of x dx plus 3 integral secant cubed of x dx. Now let me ask you something. Do I know this integral right here? Do I know secant cubed? Do I know the antiderivative of secant cubed? Yes, we've already done it. I already know what this is. It's gnarly, but I know it. Yeah? This guy right here, I can literally move over with these guys, yes? It's a little algebraic trick again. So we end up with 4 of those integrals. Do you see what I'm saying? 4 of those integrals is going to be equal to what's left on the right-hand side. And therefore, this integral of secant to the 5th of x dx is going to be equal to 1/4 of what?
Secant cubed x tangent x
Plus 3
over 2 secant x tangent x plus
3 over, so what did you say? 3 over
3 over 2
secant
x tangent x and parentheses
plus logarithm.
natural log of the absolute value of secant x, and I don't know if it's times tangent x.
No,
or
it's plus tangent of x.
It's plus tangent.
Huh? The end.
Yeah, obviously.
That's how that goes. Where did that 3? It was 1. The antiderivative of secant cubed was 1/2 secant x tangent x plus the logarithm of the sum of secant tangent. Yes. The 3 has just been tacked on to that 1/2 right there. Yeah. So let me ask you something.
Wait, where'd the 3 go to the 1?
What 3?
Oh, shouldn't there be a 3 in front of the natural log?
No, because the 3 is sitting in front of the entire
I
parentheses.
don't think there's a half in front of the natural log. There.
Hang on. So we wrote down our formula, didn't we? It was right here. Yeah, the formula for secant cubed is right here. Do you see this?
Oh, it's all part of that. Okay.
Yeah, you see that right there?
Build those parentheses in, didn't I?
That's the formula we came up with. It was just 1/2 times all that stuff. Okay. So what we have over here is correct. Okay. So let me ask you something. Is there any stopping you if it came with, if you had an odd power of secant? No, we could do the same thing. If somebody handed me secant to the 7th, we'd be able to handle that. Does that make sense? What about an even power of secant? Okay, let me just ask you this. What if it was secant to the secant squared was easy, was it not? What about secant? Hang on. What about secant to the 4th? What would you do? What would you do if it was secant to the 4th?
I mean, I guess what I would do is I would make that secant squared and switch one of those to a tangent squared plus 1 and then just do U substitution.
Mm-hmm. Okay. Yeah, that's easy, right? Okay. So you would go, okay, switch the first one. Secant squared is 1 plus tan squared, right? So you're going to put u equal to tan, and du is, okay, so this guy is going to just simply turn into u squared plus 1 du. Please, right? The even powers are easy for secant, yes? It's the odd powers that require a little bit of ingenuity, yeah? Okay. So we've seen powers of tangent. We saw tangent to the 5th. We actually were able to handle that, yes? What about like even powers of tangent? Okay, so like what if I said, hey, what's the antiderivative? We know how to do tangent. What if I said, what's the antiderivative of tangent squared?
Couldn't you just convert it to secant and then do
Yeah.
it the same way?
Right, so this would just be the antiderivative of what?
Secant squared x minus 1, and then just do that as 2.
Well, and that's just simple. What's the antiderivative of secant squared?
Tangent x minus x.
Yeah, that's easy. What about, okay, we know how to do odd powers of tangent. We already did like tangent to the 5th, remember that? What about tangent to the 4th, for instance? Just to make sure, look, I'm just pushing the envelope here a little bit, okay? What about tangent to the 4th? What would you do?
Convert tangent squared x to
Yeah.
secant squared x minus 1, and then just leave the tangent squared.
Yeah, that's right, that's right. So tangent squared of x times tangent squared of x dx. Okay, I'm just trying to make sure you guys are paying attention, okay? So tangent squared of x, and then this is going to be what? Yeah, and then we're in business. Okay, so it's the integral of tangent squared, secant squared of x dx minus the integral of tangent squared of x dx, which we just did, right? We know how to do this one. And do we know how to do the first one? Yeah, that's pretty easy. You're just going to put u equal to the tangent. Yeah. So it just seems like we've basically handled our business in just about every single case. Yeah. Yes. Maybe, but it's hard to detect. I mean, that's something you might go look up. I'm sure someone's taken the time to actually try to sort out a general formula. But no question, it's going to be really, really nasty. Okay? But you can see how they iteratively build on one another, right? You get the next one from like the previous guys or whatever. Okay?
It'd be cool if someone related to Pascal's triangle.
Yeah, I don't know. It might, but I'm not sure. Other questions? All right. So I do have one more thing I want to talk about. I'm probably going to wait to talk about it on Monday. I said that there's one situation that comes up from time to time that involves differing angles inside of sine and cosine when they happen to be multiplied together. Remember that? And there is a little trick that you have to do, and I do have a WebAssign problem that you will end up doing. I will show you briefly how to deal with that situation on Monday. But I don't want to distract from what we've done here. We know how to handle products of powers of sine and cosine or secant and tangent. That is a fantastic thing to have in our back pockets. What's going to be coming next, though, is I will show you the thing with like the differing angles in sine and cosine, but then we will actually move into something called trig substitution, which is kind of like, rather than simplifying things through a substitution, it's like you almost on purpose make it more complicated by introducing trig functions that weren't there before. But the reason you do that is because you have all these Pythagorean identities with trig functions that are really, really nice. They turn things that are sums into perfect squares. And that's going to make computation a little bit easier. So that's what's coming next. Okay? That's it.